Hello guys, today I'll be going through the factors influencing ionization energy as well as the factors influencing the atomic and ionic radii. Now many of such explanations are quite standard and so we just have to memorize them, but before we memorize them we first have to understand what it all means. Now let's talk about the factors influencing ionization energy. The first is the nuclear charge. The positively charged nucleus exerts an attractive force on the negatively charged electrons. As the number of protons increases, nuclear charge increases. Now, basically, it's the attraction between the nucleus, or more specifically, the protons in the nucleus. The protons in the nucleus here, and the electrons around it. And that's the electrons around it, you see. See, I'm just drawing with a circle, but in actuality there's no circle at all. Okay, no, because they are very random. You see the protons in the nucleus and the electrons, they experience an electrostatic attraction. So we know that more protons there are larger electrostatic attractions. That is what it means, right? That is quite simple. Okay. Now let's talk about shielding effect. Shielding effect is more complicated, but it's not very complicated, I would say. Now, shielding effect says that the electrons in the inner principal quantum shell can cancel some of the attractive forces the nucleus exerts on the outermost electrons. The more quantum shells there are, the greater the shielding effect experienced by the outermost electron. Now, what does this really mean? Now, let's draw a circle here. Now we know that there are different shells to it. Again, this is not an accurate representation. There are no circles, okay? This is what we learned in O levels, but that is wrong. They're drawing it for simple illustration. Now, electrons in the inner principal quantum shell. Now, let's say this is the outermost electron. The outermost electron is here, okay? The outermost electron is here, okay? And the innermost electrons are here, okay? Okay. Now there is an attraction between the nucleus and the outermost electrons. Okay, there's an attraction here, but the electrons in the inner principal quantum shells, basically these electrons, they help to mitigate some of the effects here, because positive, right? Positive is cancelled out by negative. Positive is cancelled out by negative, and an electron in the inner principal quantum shell is negative. So some of the positive forces is being cancelled out by this. So the electrostatic forces this experiences is less. Okay, the inner principal quantum shell, since it's closer to the nucleus, it experiences stronger electrostatic forces of attraction. So this one experiences less electrostatic forces of attraction because it's being cancelled out, and that is what it means by shielding effect. And with these two concepts, it basically helps us to cover a whole lot of atomic structure, right? These are two of the most important concepts in atomic structure: the nuclear charge and shielding effect. And the nuclear charge, effective nuclear charge equals the nuclear charge minus the shielding effect. Now let's look at a trend of IE across a period. Now the IE generally increases across a period. Why is this the case? Across a period, the number of protons increases, the nuclear charge increases. Now across a period, they have the same they have the same principal quantum shell. So basically, the successive electrons are added to the same outermost shell. Hence, the shielding effect remains approximately the same. Okay, approximately the same, not totally the same, because electrons are being added. Okay, hence the effective nuclear charge increases. The nuclear charge increases, shielding effect the same, so effective nuclear charge increases. Okay, now, and there's strong attraction And the attraction between nucleus and outermost electron increases because the nuclear charge increases, more attraction. Hence, more energy is needed to remove the outermost electron. Hence, the first IE generally increases. Now, I'll be talking about IE, well, what the definition of IE is in my definition page. So, no worries about that. There are, of course, exceptions to it. There are exceptions to it. Now, basically, the NS squared and the NS2 NP1. Okay, this one, it can be found in your notes. You can see an example there. Basically, you just write it up. And this one, there will be an extra P1 electron, okay? So actually, less energy is required to remove the MP electron as it experiences increased shielding provided by the field NS subshell. Basically, the subshell here, this one subshell, they add the shielding effect. Remember what I said just now? They add the shielding effect to it. They cancel out, so there is less attractive forces. This one can go away more easily, okay? But this one don't have. You need to directly remove the shielding effect, so don't have, okay? Then let's talk about NS2NP3 and NS2NP4. What this means? This means you basically write out, and you write out the equation, you will end at the NP, something like PX P. You need to change the like a P3 to a 1PX, 1PY, and 1PZ. Then the NP4 NP4, what is NP4? NP4 is basically, let's draw out PX, PY, PZ. We know our representation of a P subshell. We first have to fill this electron. Hence this is NP3. This one is PX, PY, PZ. Okay? Then NP3 basically means this one. This means this one. Yeah? Okay? But when we talk about NP4, right? After you fill this, where do we fill? We fill this. Oops, wrong. This is wrong. We fill this to down. Okay? Opposite direction. Okay? So basically this one, right? Then it's easier to remove this one. Why? Because it experiences what we call inter-electronic repulsion. So this guy repel this guy. This guy repel this guy. So less energy is needed. Okay? Okay. Alright, let's look at the trend of IE down a group. Now down a group, what do we know down a group? Down a group, we know the number of protons increases. What also not you know down a group? Down a group, we also know the principal quantum shell increases. Everything is increases, but we have to look at the relative increase of it. The relative increase, just like economics, the relative increase of it. But in chemistry, more straightforward. There's only one case, right? So IE generally decreases down group. Why is this the case? So the number of protons increases, hence the nuclear charge increases. As the number of principal quantum shells increases, the shielding effect increases significantly. Significantly is very important. Significantly, okay? So the outermost electron is further away from the nucleus. Okay, further away from the nucleus. Since there is less attraction, the principal quantum shell can be like located further away. Then very sad, very sad. See, very sad. Right. Hence, the attraction between the nucleus and the outermost electrons decreases, okay? And less energy is required to remove the outermost electron. The first IE generally decreases down the group. Okay? Okay. Now let's talk about the trend of IE between periods. What do we mean by between periods? Basically, right, in period 2 we know got NE. NE is over here at the far corner. Then period 3 we got NA. Okay? So yeah, this what it is what it is. Okay? So basically, right, the IE between group 18 element, which is noble gas element, and succeeding group 1 element of the next period decreases significantly. Let's look at NA. NA and NE. NA, what is the difference? Got this one. What does this make a difference? As Na has one more proton than Ne, the nuclear charge increases. Okay? And it has one more principal quantum shell than Ne. Should in fact increases significantly. Okay? One more principal quantum shell because principal quantum, look at this. Huh? Huh? The principal quantum shell. No, we're not looking at the S, we're looking at the tree. This is the principal quantum shell, okay? We're looking at the tree, not the S. Okay? S is the orbitals and stuff, okay? Excellent. So the outermost electron is further away from the nucleus in Na. Hence, the attraction between the nucleus and outermost electron decreases in Na. Less energy is required to remove the 3s electron in Na. First, Ie decreases significantly from Ne to Na. Yeah? Now, let's look at the successive ionization energy. Now, successive ionization energy, you have to go more in-depth into it. An important aspect of successive ionization energy is to know the second ionization energy and third ionization energy. And something more complex is the graphical analysis of second ionization energy and the third ionization energy. But that I have to study more. Okay. So yeah, if you guys know, can teach me. Thanks. Right. Right, let's look at successive ionization energies. Now, successive ionization energies always increases. Why is this the case? Now, we know with each successive ionization energy, electron is being removed from an ion, which becomes more positively charged. Electron removed from an ion becomes more positively charged. Hence, it is harder. It is harder to remove the negatively charged electron from a positively charged ion due to electrostatic attraction. What does this remind you of? What does this remind you of? This explanation reminds me of a certain explanation that we went through just now, which says that something becomes more positively charged. Can you identify it? Yes. Right. Let's go to the position of an element in the periodic table. It can be deduced by its successive ionization energy. What do I mean by this? Now, typically they will give you a graph. Then we identify which is the largest difference. Identify the largest difference. The largest difference. Right? So the largest difference, and the cell electron that is for example, between the 6th and 7th electron, the 6th and 7th ionization energy, when the 7th electron is removed from in the visible quantum shell, it experiences a stronger attraction towards the nucleus as it is closer to the nucleus. There are 6 electrons in the outermost shell. Now, for example, boom, 6 electrons here, boom, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Then this one, 1, 2, 3, 4, 5, 6, 7, 8. Then remove all these one. First ionization energy, second ionization energy, third, fourth, fifth, sixth. Then this one, oh shit! Remove one from the inner principal quantum shell. Hence, there will be a larger ionization energy change, So that's what it means, okay? So now let's look at trend in atomic and ionic radius down the group. Now this one is relatively simple except for the concept of ionic radius and atomic radius. Okay, they are different across a period. Now let's look at the trend in ionic radius down a group. So both atomic and ionic radii increases down the group. Why is this the case? Now, down the group, number of protons increases. Number of protons increases. Sheesh. Number nuclear charge increases. The number of principal quantum shell increases. Should in fact increases significantly. How? Then the outermost shell is further away from the nucleus. Has attraction between the nucleus and outermost shell decreases. So less attraction, the atomic radii decreases. You know what I mean? Let's go. Now let's look at the trend atomic radius across the period and the trend ionic radius across the period. They are different. Why are they different? Now they are not necessarily different in the sense you might think, because they both decreases, but they decrease for different cases. Okay, in case so atomic radius more straightforward, is decreases across the period. Why? It's relatively simple. They have three principal quantum shells. Now what? And their number of protons increases, nuclear charge increases. Successive ion electrons added to the same atomic shell should in fact remain approximately the same, hence effective nuclear charge increases. You see, all these answers are very template, okay? We just have to familiarize and understand them, okay? Familiarize, understand them, so it wouldn't be that hard to memorize them, okay? The atomic shell is attracted more closely towards the nucleus, and the atomic radius decreases across a period, you know. Right. Now, ionic radius decreases for same isoelectronic configuration. What does that mean? Now you go to your notes and you will find a diagram and you will understand it. What does it mean? So ionic radius decreases across a period. Same isoelectronic configuration. What is isoelectronic configuration? Or rather, what is isoelectronic? As when two species are isoelectronic, they have the same number of electrons. Okay, so with each isoelectronic series, the nuclear charge increases, the number of protons increases. The series of isoelectronic should in fact remain approximately the same. So when looking at a graph of 2, 2, 2, so this one is plus plus plus. We know across a period, right? The section is positive charge. Then another plus plus plus. Minus, I mean, okay, so this one is minus, so you typically have a larger one, okay, so this is what it means, okay. Now should in fact, because the process is the same, this one very template, should in fact the same, nuclear charge increases, effective nuclear charge increases, then the outermost shell, the outermost electron in the outermost shell is further away, attracted more closely towards the nucleus, hence the ionic radius decreases across the period with the same electron series. Meaning the plus increases, then the minus increases. This is what it means. Okay, now these are more tiny concepts. You see in your notes they put so tiny. But actually you look at the test 2. Test 2 got a question that needs us to know this one. Very perspicacy. They want to make this difficult for us. So we have to make this easier for ourselves. So let's look at cations. Cations with let's look at this one. Within the same period, anions have larger cation. Anions are larger than cations, as anions have one shell electron more than cations within the same period. So we just most importantly, you draw it out, you understand what these symbols mean, you can just straight away deduce. You draw this out, do. Then the one shell of electron more. Where is the one shell of electron? See, the third principal quantum shell. Then you understand already. Then the cations have smaller radii. This one need to know. Need to know why, because in the test 2 they got come out. Does it necessarily mean it will come out again? No, but you just need to know because they are very perspicacious. You need to be meticulous, you know. So cations have smaller radii than their respective atoms. Why is this the case? As there's one shell of electron less in their cations. One shell of electron less cation. Normal one, this one. Again, you write it out and you understand. This one got 3 shell, this one don't have, go away. So once the 3 shell go away, then we know one shell of electron less, so the small ionic radii. And they also have larger atomic radii than the respective atoms. This one's very simple. This one is plus, right? You take away one electron, right? If the subshell go away, right? Then bo liao. Then the ionic radii will be smaller, okay? Or the cationic radii if you want to be fancy. The anions have a larger radii than respective atom. Why? You're adding electrons. There are more electrons than protons in the anions. But this one is not necessarily about the subshell. Not necessary about this. Not necessary. It's not necessary you add one then suddenly got a subshell. Sometimes that might be the case, but no. It's a different explanation. So there are more protons there are more electrons than protons in the anions. Thus, the net attractive force for the valence electron decreases. So, for example, there are 17 protons and 18 electrons. Then the attractive force for the valence electron by the nucleus decreases. Then you take 17 proton, 18 electron, shouldn't they attract more? No, but got one extra electron. One extra electron they attract less. They got less attractiveness to it, you know? They have less sexiness to it. So the proton more further away. So they have larger ionic radii because this electron is allowed to venture more further away, and as it venture more further away, it will just make the radii larger lah. To what extent depends. If this one let's say it adds one more, the extra electron adds one more principal quantum shell, then yeah, it will increase to more significant extent. But if it doesn't, right, still it will add, but just to a lesser extent. And that is just generally what to go through in the concept of ionization energy and atomic and ionic radii. Thank you.